So, welcome back. We will start a new topic in this course that is on statistical mechanics. I will not be able to cover the whole range of statistical mechanics in details, but what we intend to do is to learn the basics of that, so that we can appreciate some derivations in later part of this course which are based on statistical mechanics. Now, in order to appreciate statistical mechanical route for connecting the thermodynamical properties from molecular pictures or molecular information, we must first get a quick recap of mathematical operations such as probabilities, and using the probabilities to connect to the thermodynamic relations. So, we will start with first probability. Okay. So, what is probability? By definition, if n is the total number of possible outcome and Na of the outcome falls in category A, then a probability of outcome falling in category A is given simply by small n A divided by capital N. This is something which we are all aware of. Okay. And I do expect that since as an engineering student you will have gone through all this exercise in the earlier part of your course, and hence this should not be difficult for you to understand it. Nevertheless, my intention is basically to give a quick recap of the terminology which we are going to use it, and later we are going to make use of this to explain the maximization of multiplicity in order to connect to the thermodynamic properties. Okay. So, in order to get there, we must first cover the basic concepts. As far as this probability of A is concerned, we know this, but then their event can have various different relations, and we are aware of this relation such as mutually exclusive. When we say the outcomes A1 to AT are mutually exclusive, it means simply that if the occurrence of each one of them preludes the occurrence of all others. What does that mean? It means that if A1 occurs, then none of 2 till T outcomes can occur. Okay. So, once A1 is there, that means this is the only possible one, that means this cannot occur at all. Okay. That is what the words precludes means. Okay. Now, in addition, we can have collectively exhaustive, which essentially means that the outcomes A1 to AT, if they are collective exhaustive, that means they constitute the entire set of possibilities. That means no other outcomes possible, okay, other than A1 to AT. Okay. In addition, we can have independent events. These are the events which, if they are called independent, if the outcome of each one is unrelated to or not correlated with the outcome of any other. So, these are the possible relationships, events: mutually exclusive, collectively exclusive, independent, okay, and of course, they could be dependent events also. Now, making use of this relation, we can also define the multiplicity. Now, the multiplicity of events is the total number of ways in which the different outcome can possibly occur. So, for example, if the number of outcome of type A event is Na, for type B is small nb, for type C is Nc, then the multiplicity W having events of type B, C, A is simply the multiplication of this number outcomes, okay, Na, Nb, Nc. Okay. So, this would be the total number of ways you can have these events in this form. Now, consider the number of possible outcome when both flipping a coin and rolling a die. Okay, these are independent events, right? Flipping a coin is completely unrelated to rolling a dice. Now, if you consider the possible outcome of the coin, there are two possible outcomes, which is 2, either you can get head or tail. Okay. And if the die has 6 faces, let us assume that is to be fair, then or if the die has 6 faces, that means you have 6 possible outcome, which is going to be 6. In that case, the multiplicity of such a events, whether when you flip a coin or roll a dice, is simply the multiplication of NA and NB. Okay. So, this is the total number of possible ways you can arrange all these outcomes, okay, of coin and the die. Okay. So, now I am going to just quickly go through the addition and the multiplication rules. If the outcome A, B till E are mutually exclusive, okay, that means if one occurs, others cannot occur, and they occur with the probabilities PA, which is NA by capital N, PB, which is NB by capital N, PE, which is NE by capital N, then the probability of observing either A or B or E, that is the union of outcomes, is simply the sum of the probabilities. Okay. So, simply the sum of the probability, that is what the addition rule would be. Now, if it is collectively exhaustive and as well as mutually exclusive, it simply means that the sum should goes to 1, okay, because that is the only possible outcomes are there. So, this would be the case when these outcomes are collectively exhaustive and mutually exclusive. In addition, we have this multiplication rule. If the outcome A till E are independent, then the probability of observing A and, now look at this, here we are putting and, A and B and C and so forth till E, which is nothing but the intersection of outcome of A given in this way in a mathematical term, is the product of the probabilities, okay, which is simply PA multiplied by PB multiplied by PE, and PA is given by this. Okay. So, this is the multiplication rule here. Okay. So, what are the example of independent events? So, for example, successive rolls of a fair die are independent. Okay. It has nothing to do with the previous roll. Okay. Or molecule 1 in position R1 and molecule 2 in position R2 in an ideal gas, when they do not interact at all, is completely independent, which means basically the molecule 1 in position R1 is not correlated with molecule 2 in position R2. Okay. But the non-independent events could be, an example would be, the roll of a die gives 1 and the same roll of a die gives 3. So, the same here refers to the roll which has been done here. Okay. So, this is like dependent event here, or molecule 1 is position R1, okay, could be, let us say if this is a reference origin, okay, and this is molecule 1, and you are asking that molecule 2 is at a nearby position R2 in a liquid. So, this molecule 2 is within the vicinity of molecule 1. So, where this molecule 2 is. Okay. So, in this case this becomes a non-independent event, it depends on the position of R1 and the vicinity of it. In addition, the combinatorics are used in probability theories. So, let me just go through the overview of that. Combinatorics is concerned with the composition of events rather than the sequence of events. Okay. Now, consider two different questions. For example, what is the probability of the specific sequence of 4 coin flips? So, specific sequence is H, T, H, H. Okay. Now, we know that the probability of obtaining the head or tail is 1 by 2. So, in this case, this is a sequence of 4 flip and each one has a probability 1 by 2. So, you are going to multiply 1 by 2 into 1 by 2, and these are independent event, okay, and this should give you 1 by 16. Now, the second question is, what is the probability of observing 3H and 1T in any order? Okay. Now, this is another question. Now, in this case we are not talking about a specific sequence here. So, which means basically if you rearrange this, okay, you can do that in so this is the probability, and then you can rearrange this in many ways, and essentially you can rearrange in 4 ways. So, you can have T H H H H T H H H H T H and H H T H H T. Okay. So, there are 4 different ways. So, each one is 1 by 16, okay, and you can add this, this will give us 1 by 4. Okay. So, 1 by 16 multiplied by 4, okay, this was going to give you the answer 1 by 4. So, we will discuss is how you can solve this particular one using permutation or the binomial distribution. Okay. Now, there is the objects or the events or many times are distinguishable and non distinguishable. So, let us consider objects which are distinguishable. For a sequence of n distinguishable objects, the number of different permutation is simply expressed as n factorial. Okay. So, for example, if you have a distinguishable letters such as y, w, x, w, y, w, x, y and z, then how many permutation of different sequences of the letter can be possible? So, considering as a distinguishable, you can simply say is 4 factorial. But if it is not distinguishable, then of course, there are other issues which we have to take into account. So, in order to express that, we will combine this distinguishable and indistinguishable object together. Let us consider a collection of n objects with t categories, of which ni objects in each category are indistinguishable from one another, okay, but distinguishable from the objects in the other t minus 1 category. What does it mean? That you have n objects which can be segregated in different categories, and in each these are not distinguishable from each other, but this one is distinguishable from with the other one. So, this is let us say category 1, this is 2 and this is t, and in each one you have n 1 object, in this case is n 2 object and is this n t object. So, n 1 is of type 1, n 2 is of type 2 and so forth, n t is of type t. Among n t, all are of same type and thus cannot be distinguished from each other, cannot be differentiated from each other. On the other hand, an object from t category can be differentiated from object from 2 category, for example. So, in such case, what is the permutation? That means, how many ways you can arrange such an objects. Okay. So, if it is distinguishable, this would have been simply n factorial, and then since these are the groups which are can be segregated, and among these are indistinguishable. So, we are going to divide it so that we can correct this number of possible ways. So, in this case it will be n 1 factorial divided by n small 1 n 1 factorial, small n 2 factorial and so forth, which is to avoid or to correct the overcounting. So, this is the permutation of W in such a case. Now, we can express this understanding in an example. So, for example, how many permutation or different sequences of the letters in the word are there? So, if you look at it here, you have 1, 2, 3, 4, 5, 6. So, there are 6 letters, okay, and then you have category C, H, E and S. This is 1, this is 1, E there are 3 of them and S there are 1. So, in this case you have W as 6 factorial divided by 1 factorial, 1 factorial, 3 factorial 1 factorial. So, this is the number of possible way, which is going to be 6 into 5 into 4, 120. Okay. So, these many permutation or different sequences of the letter you can arrange here. So, let us consider a case where you have only 2 categories such as success, failure, heads, tail, yes or no. So, in that case, if t is only 2, that means you can write w small n, which corresponds to success. That means the number of sequence with n success out of n trial can be written as simply n factorial divided by n factorial multiplied by n minus 1 factorial. So, you could have also written something like this, n factorial n 1 and n 2, okay. But n 2 is nothing but n minus n 1, and thus you can plug in here to get this expression. So, this is relevant when you have only 2 categories outcome of the events. Now, let us go back to the earlier question where we said we wanted to find out the probability of observing 3h and 1t in any order. Okay. So, we can actually do the same exercise. So, we have this 1 by 16 was the probability of getting t h h h, let us assume that, and then you can multiply by having the number of such possibilities, which would be simply w 3 4, which is nothing but 4 divided by 3 factorial, and this is 1 factorial, which is nothing but 4. So, this would have given simply 1 by 4, the same answer which we got earlier. Okay. Okay, so now what we have discussed this combinatory, we are going to extend this exercise and express the probability in this form, where this is pi as a function of various different event outcomes. So, I could range from, let us say 1 to 5. So, let us assume this to be a mutually exclusive outcome, okay, and these are the numbers or the values of such an outcome. Okay. This is an arbitrary value for a given set of events which we know, okay, just for the sake of examples. Now, because these are mutually exclusive and collectively exhaustive, that is, sum of this should yield 1, okay, which would be the case if you add it up here. Now, this was a very discrete event. For a continuous probability distribution function, which would be in many cases, this becomes the case. This is usually where the system is not cannot be categorized in some discrete events. In that case, we usually give a probability in a continuous form using a variable x here. Okay. So, probability in that case is the p x multiplied by the differential element of x. Okay. If x is continuous, then we call it p x as probability density. Now, the probability density in general, the probability distribution should be normalized in for a given range, and hence you need to make sure that integral of p x from a to b should be 1, and thus if you want to normalize p, normalized value should be p of x divided by the integral, okay, from a to b. So, this would be a normalized version of it. Okay. Now, that is what we are saying here, normalizing distribution. If a continuous distribution function, let us say, is not normalized, we define a normalized constant, which is simply the integral version of this, or integral of psi x from a to b. Then we normalize this function by dividing psi of x divided by this constant psi 0. Okay. So, it is a very straightforward exercise. Now, we will extend this now, this distribution, this continuous distribution function for binomial and multinomial distribution. Okay. So, let us first discuss binomial distribution. Here we are interested in only 2 events which are mutually exclusive outcomes. So, let us consider here in which independent elementary events are filled circle and empty circle. These are mutually exclusive outcomes. So, let us say for this filled circle event, the probability is p. Okay. Now, since it is a mutually exclusive, whatever the probability of this can be now written as 1 minus p, because summation of these two probabilities should be 1, considering is to be mutually exclusive and as well as exhaustive, okay, collectively exhaustive. So, now the binomial distribution is given as p small n, n is total number of outcomes, n is the outcome of specific type. Now, which we are interested in this case is the outcome of the events having filled circle. Okay. So, the binomial distribution gives the probability of observing n filled circle and n minus 1 empty circle in any order when performing n independent events. Okay. So, the way we write is the following, that since this is n, small n, the probability of this is going to be p multiplied by p of n times. Okay. And similarly, for the case of empty circle, it will be 1 minus p n minus 1, okay, considering these are independent events. But now you can arrange this in many ways. So, using the earlier expression of the permutation, we are going to consider these are only 2 events. So, it is going to be n factorial divided by the small n, the number of events or the objects of type circle would be small n factorial multiplied by n minus 1, the remaining one are of type empty circle. So, this becomes a simple binomial distribution function. Now, if you go back to the original question, that how many ways or what is the probability of observing 3 heads and 1 tail. So, this will be, so if you go back to the original question of 3 heads and 1 tail, the probability of head or tail is 1 by 2. So, in this case let us say this is p 1 by 2 and we are talking about 3 head. So, it is p 3 4, okay. That means 3 heads and 4 is the total number of events here. This would be 1 by 2, again 1 minus p is 1 by 2, n minus 1 is 4 minus 3 which is 1, this is 4 factorial, small n is 3 factorial and this is 1 factorial. So, this is going to be 1 by 16 multiplied by 4 is 1 by 4. So, you get the same expression as we have discussed it earlier, okay, using this binomial distribution function. Now, similarly, we can find out by changing these 3 to 2, 3 to 2, 3 to 1, 3 to 4 and this kind of distribution we can get. Okay. So, I am not going to derive this, but it is obvious that once you have done this exercise for the case of 3 heads, okay, where we got 1 by 4 in the answer, you can use the same exercise to obtain the probability for different cases as shown in this plot. Okay. Now, I can generalize this binomial distribution function to multinomial distribution function. So, a multinomial distribution function applies to t outcome events where ni is the number of times that outcome I from 1 to t appears. So, instead of 2 events, now we have n events. So, you are going to multiply p 1 n 1 p 2 n 2 and p t to the power n t. These are the t outcome events, okay. And then we multiplying the number of ways we can arrange these events, okay, which is going to be n 1 factorial divided by the number of objects of type different types. So, n 1, n 2 and n t. So, this is a multinomial distribution function, okay. Now, given a distribution function, we can obtain the average value and standard deviation, which is commonly done in statistical mechanics, and thus we must know how to calculate it. So, we are going to use the moments of the probability distribution function to calculate the average or the mean values, or in general the standard deviation also. So, let me just define that given a function p of x, okay, the nth moment of the distribution is defined as this. So, this is the average x to the power n indicates the nth moment. So, 0th moment would be this and one moment would be this, okay. Second moment would be this, okay. So, let me just describe this little later, that how does we explain this, but let me first come up with the definition of x n. So, the moment nth moment is nothing but the x to the power n multiplied by the probability, it is like a weighted average, okay. But then you are considering x to the power n. So, this is a normalized version, and that is why you are writing x to the power n psi of x, which is a non-normalized probability distribution dx divided by the normalization constant. So, we have written this is x psi 0, okay. So, which means basically average of x, the mean value of the x using the distribution is going to be x p x dx, okay. And that means this p of x dx is going to be simply x 0, okay. So, the 0th moment is always equal to 1 if it is normalized, of course, it is going to be 1, and the first moment is called the mean or the average or expected value. Now, let me also define the variance. The variance sigma square of a distribution is a measure of the width of the distribution. The variance is defined as the average square deviation. So, this is the average. So, this means average square deviation means x minus a, which is mean value of this square of that. So, this becomes the variance of that, okay. Alternatively, you can also show using the properties of this angle bracket, which is a mean value, that this sigma square is nothing but the mean value of x square minus the square of the mean value x, okay. So, that is variance of that. Okay, let me end this lecture by just doing this final exercise of evaluating the average value of x for a given flat probability distribution and as well as for non-flat probability distribution. So, this is the probability distribution given to us, which is 1 by a as a function of x, which is a flat, that means it is a constant, and we need to find out x here, okay. So, this is going to be x p of x dx divided by p of x dx. So, I do not know whether it is normalized. So, we have to first make sure that it is normalized. So, this is nothing but 1 by a times a is 1. So, certainly this is normalized. Now, this can be shown, this is as 0 to a x, p x is 1 by a dx, which is nothing but x square by 2 a, and x is nothing but 0 to a. So, this is nothing but a by 2, okay. So, that is what we can get here. Similarly, you can show this that for such a system or such a probability distribution, the average x is nothing but 1 by a here, okay, in a similar exercise. So, with this I believe that we have got the basis or the foundation for us to use this understanding to take it to the next stage, where we are going to show that maximizing multiplicity, that is W, can be related to the entropy, okay, and from there we can connect to the macroscopic properties, okay. So, I will see you in the next lecture, continue with this exercise.